Project 2.2.3 ISP.Long Ultrasonic Radar Scanner. For my ISP project, I built an ultrasonic radar scanner. The system can detect objects, measure how far away they are, and which direction the object is across a 180-degree plane. This is the functioning device. The ultrasonic sensor sweeps across an arc using a servo motor. At each angle, the system measures the distance to nearby objects and displays that information visually on a plan position indicator. Here is my device's block diagram and flowchart. Either using a terminal block or by plugging in the Arduino, you can give power to the device. An internal voltage regulator will regulate this power to 5 volts. The first part of the device is the microcontroller. The microcontroller used is the Arduino Nano. The Nano adds a complete support and interface system around the ATmega 328P microcontroller, allowing it to be easily programmed and used without complex external circuitry. The microcontroller functions as the control unit responsible for timing, data acquisition, signal processing, and communication between peripherals. This is the ultrasonic sensor, which is responsible for measuring distances. It works when the microcontroller flashes the sensor's trig pin high, resulting in the sensor sending out a burst of high-frequency sound waves that humans can't hear. These waves travel through the air, hit an object, and bounce back to the sensor. After the pulse is sent, the sensor's echo pin goes high and only goes low once received. By timing this high pulse on the echo pin, we convert time into distance using the equation you see on screen, which multiplies it by the speed of sound in centimeters per millisecond and divides it by 2 since the sound waves must travel to the object and back before returning. Now onto the display. This is an OLED, organic light emitting diode display, which is a flat panel display technology in which each pixel produces its own light. Unlike LCD displays, OLED screens do not require backlight, allowing them to be thinner. The OLED was useful for the PPI, plan position indicator, in this project since it produces a clear visual output while using minimal power. A plan position indicator is in the map display you saw at the start of the video. An example will be flashed on screen. Most small OLED modules communicate with microcontrollers using the I2C protocol. I2C uses only 2 data lines, SDA data and SCL clock, in addition to power and ground. This protocol allows multiple devices to share the same communication bus while using unique addresses. This diagram illustrates the structure of a complete I2C message. Communication begins with a start condition generated by the master device, the microcontroller. This occurs when the SDA line transitions from high to low while the SCL line remains high. Following the start condition is the address frame, which identifies the target device. After each byte is transmitted, the receiving device sends an acknowledge ACK bit by pulling the SDA line low. That confirms the data was received. If the device does not respond, a not acknowledge NAC bit is sent instead. Once the address is acknowledged, the master sends one or more 8-bit data frames, which present control commands, pixel data, and more. Here is one of the beginner projects I did back in November to test and gain understanding on 2 components. It is ultrasonic rangefinder, and it simply measures distance and displays it on an OLED. The final component of our device is the SG90 servo motor. The microcontroller will send a PWM pulse requesting a certain angle depending on the pulse width. The servo converts pulse width into a reference voltage. The potentiometer then connected to the motor will rotate itself along with the servo motor until the voltages match, which means we've reached our desired angle. Here's the final one of my 2 beginner projects I did back in November. It's a spinning RSGC flag which uses the servo to rotate. Depending on which direction the flag is being spun, a different LED turns on. This is the final ultrasonic radar scanner prototype. And finally, I converted my prototype into the final device. On screen, you see my fusion case and PCB design. The objective here was to create a nice compact device that was visually appealing. Now on to the most intense part of my project, the software. I'll walk through my ultrasonic radar scanner code and explain how each section works. First is the libraries. I include servo.h to control the servo motor, wire.h for I2C communication, and the Adafruit GFX and SSD 1306 libraries to control the OLED display. I also include math.h so I can use sine and cosine to draw the radar sweep. The ultrasonic sensor uses trigger pin on pin 3 and an echo pin on pin 2, and the servo motor is connected to pin 4. Then I configure the OLED display. I define the screen width and height and create an Adafruit SSD 1306 display object. The OLED OK flag lets the program know whether the display is initialized correctly. The radar settings come next. I define the maximum detection range and the radar radius in pixels. I also set up arrays called PERST-ING and PERST-DIST to store previous detections, which creates the fading persistence effect on the screen. Below are the interrupt variables. These volatile variables store the start and end time of the ultrasonic echo pulse. They're marked volatile because they're modified inside an interrupt service routine. In setup, I initialize serial communication, set pin modes, attach the servo, start I2C, and initialize the OLED. I also display a short startup screen and attach an interrupt to the echo pin so the timing can be measured precisely. In loop, the servo sweeps from 0 to 180 degrees and then back again. At each angle, the code triggers the ultrasonic sensor, measures the distance using interrupts, prints the data to serial, and calls draw radar to update the display. Echo ISR records the exact time the echo pulse starts and ends. Trigger pin sends the 10 microsecond trigger pulse to start a measurement. Read distance interrupt covers the echo time into distance using the speed of sound equation. Finally, draw radar clears the screen, draws the radar circle, the sweep line, and plots detected objects using trigonometry. It also displays the current angle and distance in text at the top of the screen.